Now we come to arguably the most important probability density functions in the course, the normal curves. So recall from calculus, or what I said in another video, that no general formula is known for the integral of e to the c x squared dx, where c is a constant. Let's say we're integrating from a to b. It doesn't matter what the, well, almost doesn't matter what the numbers are. We don't have a general formula that works for all pairs of numbers a and b. We do have a special case, though. When c equals -1/2. So we have a formula in this special case. So when we're integrating from -infinity to infinity and c is -1/2, that turns out to be square root of 2 pi. So if we divide both sides of this equation by 2 pi, that means that 1 by square root of 2 pi, 1 over square root of 2 pi, integral from -infinity to infinity, e to the negative, let's say x squared over 2 dx equals 1. And this function's always positive because it's got the x squared in there. And actually e to a negative power, not because x squared, it's because e to any power is positive. So if we define this function f of x 1 over square root of 2 pi e to the negative x squared over 2, this is a probability density function. Always positive and has area 1 underneath the curve. So it looks a little bit like this. The curve is also called the Bell curve. All right, so let's say we choose a point under here. So let's say capital X equals the x coordinate of a randomly chosen point. Under the curve. So we call x a normal random variable. Actually standard normal. And we write x is distributed as n, 0, 1. The expected value of x is 0 and the variance is 1. Now even though e to the negative x squared over 2 is hard to integrate, and we need to integrate to get expected value and variance, these integrals aren't hard. because if we want the integral of x times e to the actually any constant cx squared dx, x is pretty close to the derivative of cx squared. We just need to multiply by a 2c inside and divide by 2c on the outside, and this is easy to integrate. So that's easy. And then, so that gives expected value of x, and then we would need expected value of x squared, and we would integrate something like e to the x squared e to the cx squared dx. Not super easy, but if we write it as x times x e to the cx squared dx, then we can do this by integration by parts. So we can do those integrals and get the expected value of variance. So again, so this function here is the standard normal curve, and that's 1 over square root of 2 pi e to the negative x squared over 2. And there's variations of this that are taller and skinnier and shorter and fatter. So we can look at the variation 1 over square root of 2 pi, I'll put a number sigma here, e to the minus x squared over 2 sigma. Oh, sorry, sigma squared here and a regular sigma in the fraction. So when sigma is small, then we get a taller, skinnier bell curve. And when sigma is large, we get a shorter, fatter bell curve. So when sigma equals 1, then dividing by 1 here and dividing by 1 there gives us the standard normal curve. So by small I mean less than 1 and here greater than 1. And I'm thinking of sigma as a positive number. Then we can shift this curve around to the right or the left. Oh, I should mention the variance here. So this, here we have, so if x is choosing a point under one of these curves, then expected value of x is still 0. Variance of x is now sigma squared. So that number that we divided by here, well, sigma here, sigma squared there, gives us the variance. Now we can move the curves to the left and right also. We do that by replacing x by x minus mu. So this is going to be the bell curve that's centered at x equals mu. Here the expected value of x is mu, and the variance of x is still sigma squared. So again, I'm thinking of x as the x coordinate of a randomly chosen point under the curve. Now the standard normal curve is centered at x equals 0 and has variance 1. These are all normal curves. And the random variables are called normal random variables. It's called the normal random variable. And we write x is normal with mean mu and variance sigma squared. So it's standard normal if mu equals 0 and sigma squared equals 1. All right, so another maybe natural question to ask is, where do normal curves arise? And the answer is almost everywhere. So to be explicit, suppose we repeat trials of any experiment. So let's let yi be the outcome of the ith trial. Let's say the expected value of yi is mu. So these are all identical and independent. Variance of yi is sigma squared. So they could be Poisson random variables or binomial random variables or geometric random variables or other normal random variables, anything at all. So suppose we repeat the trials, and let's consider the random variable that we get by taking the average of all the trials. So we do n trials and we take the average. So then this is a random variable itself. So this has the approximate distribution, which gets better and better for n getting large. Of normal random variable with mean mu and variance sigma squared over n. So we started with random variables that had mean mu. The average still has mean mu. The variance was sigma squared. Now the variance has gone down by a factor of n, so sigma squared over n. But the amazing thing is it doesn't matter whether we're doing Bernoulli trials or binomial or geometric or hypergeometric or negative binomial, anything. No matter what distribution we use, as long as we keep doing the same trial over and over and take the average, it's approximately normal, with the approximation getting better as n gets larger. Now, we'll talk more about this fact at the end of the course. In fact, this fact is not in the section we're doing now, but I just wanted to tell you the reason that it's worth studying the normal distribution, because it's really universal, it's everywhere. Alright, so let me tell you some good and bad news about the normal curve. The bad news, I guess we've already said. So, functions of the form e to the cx squared are impossible to integrate. Well, unless c equals -1/2, and we're integrating from negative infinity to infinity, and maybe a couple of other courses, but a couple of other cases, but generally we can't integrate this. So the good news is that you can do this by computer, and in fact other people have done it by computer. So we can look up integrals in tables. So tables of values of integrals are very common. You can look them up in any probability book. In our textbook, they're on page 204. So you've got a big table of numbers like this. So we can't integrate, but we never have to. We just look things up in a table. There's only one table there, and there's lots of normal curves. As we let mu and sigma vary, we get this infinite family of normal curves. So the table is built for the standard normal curve with expected value 0 and variance 1. But that's not a problem, because if we have a distribution that's normal but not standard, we can play with it a little bit and still use a standard normal table. So recall that the expected value of ax plus b, so if x is a random variable and a and b are constants, is just a times expected value of x plus b. And the variance of ax plus b is a squared times the variance of x. The additive constant plus b here doesn't affect the variance. Now if x is normal, so is ax plus b. It's just spread out or scrunched up and shifted a little bit. I just say normal, if it's got a normal distribution, then so is ax plus b. So just spread out or squeezed shifted. So if x is a normal random variable with mean mu and variance sigma squared, then ax plus b is normal also, but the mean is now, let's see, expected value is going to be a mu plus b, and the variance is going to be a squared times sigma squared. So in particular, if we choose a and b carefully, we can get a 0, 1 standard normal variable. So what happens if we take x minus mu and divide by sigma? So that's x over sigma minus mu over sigma. So a is 1 over sigma and b is negative mu over sigma. So this is normal with mean a, we said, is 1 over sigma. So mu over sigma plus b minus mu over sigma, so that's going to be 0. And variance a squared sigma squared. So a is 1 over sigma, so a squared sigma squared, which is the standard normal variable. So this means suppose we want the probability that x is less than or equal to a when x is a normal variable with mean mu and variance sigma squared. Then we can play with this. We'll subtract mu from both of these and divide both by sigma. Then this expression, x minus mu over sigma, is a standard normal variable. So we could say this is the probability that z is less than or equal to a minus mu over sigma for z, a standard normal variable with mean 0 and variance 1. All right, let's do one example with numbers. So let's suppose x is normal with mean 10 and variance 2. So it looks something like that. Let's find the probability that x is between 8 and 12. So this area here. Now by symmetry, the normal curves are all symmetry. This is the same as finding 2 times the area between 10 and 12. Which is 2 times the probability that x minus 10 divided by square root of 2. So 2 is sigma squared, the variance. We're dividing by square root of that. This is the expected value, mu. So this is between 12 minus 10 over root 2 and 10 minus 10 over root 2, which is 0. Twelve minus 10 is 2. 2 over root 2 is root 2. So z is a standard normal variable. So now we just need to look in the table to see what's the probability that z is between those values. Now remember, the standard normal curve is centered at 0. So the probability that z is greater than 0 is half. We have 50% of the area on this side and 50% on that side. So this is 2 times something minus a half. Actually, I guess I really mean the half on the left, because if this is 1.41, the table is going to give us area less than that, and then we subtract this half. So we need to find the area to the left of 1.41. So in the table, we see 1.4 over here. The way they do it is they give you an integer point one place past the decimal, and then 0.1 is a column, and then right here in this entry, this is the 1.41 entry. So it turns out it's 0.9207. So in the book I see 0.9207 there. So 0.9207 minus 0.5 times 2 is 2 times 0.4207, which is 0.8414. So the probability that x is between 8 and 12 is 0.8414. So what we have to do by hand is subtract the expected value and divide by square root of the variance. And then once we get these fractions simplified, we have to put them in a decimal form. Then we can look up that decimal in the table, and we get the probability that we're looking for. The end.